Hello students, welcome to the discussion on evidences of nucleosynthesis. So, let me take a quick recap of the previous lecture in which I have discussed more evidences for nucleosynthesis like the measurement of light curves from supernova, the decay of cobalt 56 before reaching nickel 56, how supernova theoretical models predicted the light curves, and experimentally there was a good agreement. And in the last lecture I have also discussed one of the fascinating problem in nuclear astrophysics, that is how mass numbers at 5 and 8 can be bridged. The gaps at mass numbers 5 and 8 can be bridged based on the concept of triple alpha process. Do you remember the last lecture's ending part where I have shown you chart of Fu nucleates and there were no stable isotopes for the mass number 5 and 8, and that is where the fantastic contribution from the Hoyle, who predicted that it is because of the resonance at around 7.7 MeV level in carbon 12 leads to the production of carbon 12. If the fusion between alpha and beryllium 8 does not happen around the Hoyle state, then the observed abundance of carbon 12 could not be explained. So, that is where we have seen it is a two-step process, and that two-step process which has led to the production of carbon 12 could answer the question, one of the important questions in this course, that is how to understand the gaps at mass numbers 5 and 8. So, after this, in today's lecture we are going to discuss one more important selected evidence, selected property of the universe, that is how one can see the variation of luminosity, temperature, density and color of stars in the universe. Okay? So, with the help of HR diagram, the name of this selected property of the universe is HR diagram. In today's lecture we will see some more features. Okay? Let us start. So, let me discuss second important selected property of the universe. First important selected property was elemental abundance curve. Second one is HR diagram. You might have seen in the internet about this HR diagram. Okay? What it tells us, how it is helpful to us. See, the objective of this course is to understand the nucleosynthesis, that means how elements are formed in the universe. And what is the second objective? Energy produced from stars. What is the reason behind the production of energy from the stars? And it is very clear that it is the nuclear reaction which is playing vital role in the production of energy from the stars. So, it is quite natural to understand the properties of the stars. So, how to understand the properties of the stars? There are various types of stars. Is it possible to categorize the stars based on their intrinsic properties? So, Hertzsprung and Russell, these two researchers independently, what they have done is following, which is very interesting. Please pay attention. Okay? See, in order to understand the properties of the stars, you need to correlate the intrinsic properties of the stars. And when I say star, which is an entity having large number of nucleides, okay, it is some kind of plasma, you can say. So, each star has its own temperature, its mass, size, chemical composition and luminosity. Here you need to remember the luminosity is ranging from 10 to the power of minus 4 to 10 to the power of 6, about 10 to the power of 10 difference, right. So much difference, whereas the temperature is 3000 to 15,000 Kelvin, and mass range also have been given in one of the earlier slides. So, the luminosity range is quite, it is quite wider. It has a huge range regarding luminosity. So, this Hertzsprung and Russell, what they have done independently, experimentally whatever luminosity was measured, they tried to plot with respect to the temperature or color of the star. So, what is this color? I will give you more details in coming slides. So, you take a star, measure its luminosity, that means energy per emitted per unit time, and what is its temperature? You plot the variation of luminosity with respect to temperature, then you see how stars are arranged. Initially people expected they will be distributed uniformly throughout the region of this luminosity versus temperature, but surprisingly it has given totally a different kind of scenario. What is that? See here. See, luminosity when compared to sun on y axis, on x axis spectral class, that means color. What is the meaning of this color? What it corresponds to? I will discuss in the next slide. Okay? And absolute magnitude on the y axis, left hand side, and effective temperature on the x axis. So, this kind of diagram you may not have seen very frequently, but it is quite possible when one wants to correlate 4 properties in the same diagram, they can plot like this. I mean, they can consider the quantities like this. So, the more details can be obtained from this diagram or any source in the nuclear astrophysics textbook can be seen this kind of diagram. So, because I found it more colorful, I took it from this website. Okay. So, what is so specialty about this diagram? The relation between these quantities like luminosity, temperature mainly. Of course, in this list I have not included the magnitude and spectral class, because mainly luminosity on the y axis and on the x axis temperature I have denoted. Fine. When these people have plotted these relations and independently studies were done way back in 1912, you see by that time nuclear reactions, all those things, studies were not very clear. Simply the data of stars were available, like what is its temperature, what is its color, what is its mass, what is its density. From the spectral analysis, from the whatever light is emitted from the star, people have measured the spectrum, and from that spectrum using some mathematics and some techniques, they have measured the quantities like temperature, mass, luminosity, all those things. And Hudspun and Russell, they have taken those values and they have plotted. Okay? And here I am using a word absolute magnitude. See, experimentally when we measure, it is basically apparent magnitude. To convert into absolute magnitude, from the apparent magnitude, people take the help of one unit called as parsec. Okay? So, 10 parsecs is equal to like 32.6 light years. So, I am not going into the details of the conversion of apparent to absolute. Okay? Anyway, the important features are following. Stars are not uniformly distributed throughout the region of temperature and luminosity. Stars are not uniformly distributed. It personally it remains to me. It reminds me that the distribution of mass of an atom before the discovery of nucleus by Rutherford, how people used to think the mass is distributed throughout the atom, right? Thomson-Plum-Pudding model. The moment Rutherford did the famous alpha scattering experiment, then people got convinced, no, mass is not, atomic mass is not distributed uniformly throughout the atom, but it is concentrated at the center of the atom, that is called as nucleus. 99.99% of the mass is concentrated at the center of the atom. Anyway, coming back to this stars business, the stars having different luminosities, different temperatures, they are not distributed uniformly throughout the region as expected, but majority of the stars, they are following a narrow sequence. See this diagram, narrow sequence, main sequence. Where is it, my dear? You see here, the black one I am drawing. This is main sequence. Starting from blue, can you see the blue color on the left side? Very hot, high temperature, 10 to the power of 5. Blue, hot, high luminous, okay, upper left. So, this sentence is very important. Upper left of the diagram, if you see, they are blue. So, the stars which are emitting blue, that means they are very hot, high temperature, around 30,000 kelvins. and high luminescence, luminous stars. Okay. Stars are distributed, majority of the stars are distributed from upper left to bottom right. So, for your convenience, upper left I have denoted with blue color, and bottom right I have denoted with red color. The stars in the bottom right, their color is red. In terms of temperature they are cool, and in terms of luminous it is less luminosity, and the majority of the stars are lying between these two, around 90%. Isn't it very interesting? 90% of the stars, they possess luminosity and temperature in the main sequence, and not only that, there are stars not only on the main sequence, remaining around 10% of the stars, they are clustered into several groups, like one group is red giants. So, as the word says, it is in the red region, but as the size wise it is very large, high volume. So, you can see in this diagram giants, okay, and if you go above this, super giants, they are high, they are hot, but color is red, okay, but temperature is luminosity is very high, temperature is less, low luminous, okay, low luminous, red color, okay, red color, low temperature, high luminous. Okay. So, the red giants, above that you have super giants who have luminosity very high, like 10 to the power of 5, temperature very less, like 4000, and color red. How these red giants are formed, I will discuss in detail in coming lectures. Okay. For time being, the purpose is to show you that stars are not distributed throughout the region of luminosity versus temperature, but they are grouped into several clusters. One of the main clusters is main sequence, another is giants and super giants, they are red in color, so we call them as red giants. Okay. And then we have white dwarfs. Okay. White dwarfs, they are blue and hot, but low luminous. Okay. What are white dwarfs? Blue, temperature is also very high, okay, these white dwarfs, and low luminous. Stars are clustered into three major categories. Number 1, main sequence. Number 2, giants, red giants or super giants. Then number 3, white dwarfs. So, if you have 10 stars, I mean if you have say 100 stars, 90 are on main sequence, and out of remaining 10, some are in red giants and super giants, and remaining are in white dwarfs. So, what this tells us? See, in order to understand the construction of the star, if you want to model the star, how star is forming could be something common, but what is happening after the death of the star, that can go to white dwarfs, that can go to red giant. So, this evolution of star, to understand, HR diagram proved to be one of the excellent tools in the nuclear astrophysics. For better understanding, let me give you some numbers in terms of luminosity and temperature. But when I am going to the next slide, please remember that main sequence starts from blue hot high luminous to red cool low luminous, along which main sequence, along this main sequence 90% of stars are there, and white dwarfs are blue hot low luminous stars are there, and regarding red giants, high luminous, cool but red color. And let me give you some more numbers so that you can enjoy this HR diagram in a better way. Okay. See, star type, sometimes you can see O star, B, A, F, G, K, M. This kind of codes are given, okay, and color, it could be blue, okay, or blue to white, the transition, white to yellow, orange to red, and red finally. And let me go to the previous slide. See, you can see here O, B, A, F, G, K, M. These codes corresponding to these colors, and corresponding to each color, the surface temperature approximately ranges from 25,000 to 3500, Are you satisfied? Earlier I have given you 3000 to some kind of 50,000 kelvins. Here I am showing up to 2500 kelvins. Okay. Average mass when compared to the sun, if you see, it ranges from 0.3 to 60. Okay. And near sun, if you go, it is orange to red and white to yellow. So, where is the sun in the HR diagram? You can see here. Sun in the HR diagram is given here. Okay. And compared to sun, the average radius is 15 times in the upper left and 0.4 times to the sun radius in the bottom right. And in terms of sun luminosity, if you see, it is about 14 lakhs, okay, 1.4 million times that of sun. These are the stars in the upper left region and very faint 0.04 times that of sun in the red, cool and low luminous. Okay. So, this table gives us an idea of regarding the numbers for temperature, mass, radius and luminosity. And whenever you see this kind of codes, it denotes the color code in HR diagram. How it is going to be useful for us, this HR diagram? Let me give you some calculations. Okay. See, main sequence with luminosity of 1 and a temperature of 5400 K, that is sun, right. Sun has a luminosity of 1, we can consider, and whose temperature is 5400 Kelvin. We have to have some reference, right. And assuming the black body radiation, the Stefan's law tells us the luminosity is proportional to 4th power of the temperature. So, this is playing an important role in understanding the construction of the stars. Let me take the help of this Stefan Boltzmann's law. Now, if I go for ratio of luminosity of a star with respect to luminosity of sun, so r square T to the power of 4, right. Ratio of radii and ratio of temperature, straightforward. L by L naught is equal to r by r naught square into T by T sun to the power of 4. Let me take upper left hand region. In the upper left hand region, the L by L naught is 10 to the power of 6. In the table also I have shown you this order 10 to the power of 6, around 1 million times in terms of luminosity. If L by L naught, L sun is 10 to the power of 6 and T by T sun is about 4 for upper left hand, the size of the star is given by this value. So, one can find out the size of the star if luminosity is known, temperature is known. That is the beauty of HR diagram. I found a star, I do not know its radius, I do not know its size, no need to measure the size directly. This HR diagram gives you direct tool about it, tool to measure the size of the star. So, the size of the star can be measured if you can measure the luminosity of the star and the temperature of the star. So, go with the relation and you will get very good idea about the size of the star. All right. Let me discuss more about this. Upper right hand, okay, that is red giants. L by L naught is 10 to the power 4 high luminous, of course low temperature, that is the reason I have written T by T sun is 1 by 2. See the HR diagram, it will be more clear to you. Keep HR diagram with you, because okay, otherwise these numbers will be confusing to you. This gives radius very high, 400, you see, that is the reason I have used a word red giants, very big size. How much? About 400. How this number we got? Just by looking at the ratio of the luminosity and the temperature, okay. And it is truly giant, right. R by R sun is 400, R by R sun is 60 only, upper left hand. From this, can we find out the density ratio? Of course, you can find out the density ratio. It is less than or equal to 10 to the power of minus 6 if the mass ratio is 50. So, if you know the mass ratio and if you know the radius from the HR diagram with the help of L by L sun and T by 2 naught, you can get the idea of R by R naught, and from the mass you can find out the density. See, extremely less density, very low mean density for upper right hand for red giants. So, how this red giant stars can be formed from the star on a main sequence? A star on main sequence can become white dwarf or it can become super red giant. When it can happen? Which kind of nuclear reaction is playing important role in it? Those things I will discuss in another part of the course. Okay? So, for remaining main sequence stars, please do it yourself, especially in lower right hand and lower left hand, that is for the white dwarfs. I have done only for the super red giants. Please do it for the white dwarfs. Take the values of L by L sun and T by T sun. Okay? Now, one of the important applications of this HR diagram is following. See, if I want to measure the stellar distances, if I want to measure the distances between stars, there is a interesting indirect method. What is that? On Earth, you measure the spectral class or color. Do you remember earlier in the table I have given you spectral code O, K, M, J, like that, fine. So, you measure the spectral class or color, from that you find out the luminosity from HR diagram. Once you know the color of the star, you can go for the luminosity. Please try to understand this, because many assignments and numericals are based on this concept. Okay? So, once this luminosity is known, with observed brightness one can go for the distance of the star by comparing with the observed brightness. Okay? This is called as method of spectroscopic or photometric parallaxes. Okay? So, this is one of the important applications of the HR diagram. And let me complete this topic of HR diagram by giving you a mathematical relation between luminosity of a star and the temperature of a star. It is about 5.5 in the power. Luminosity is proportional to surface temperature to the power of 5.5. Okay? And the utility of the HR diagram is, as I said, by finding the position of a star, one can get the information of the internal structure of the star and how star will evolve. The stellar evolution is one of the important objectives of this course, right? How star will evolve? It will go to red giant or it will go to white dwarf. It is easy to guess if you understand the HR diagram. So, to summarize, in these two lectures, what I have done, I have provided few more important evidences of nucleosynthesis, that is detection of neutrino, and one important facility also I have shown you in Japan. Number 2, another strong evidence, decay of cobalt 56, with respect to which people have calculated the light curves of the supernova, and they are in very good agreement with the experimentally measured the light curves of the supernova. Then I discussed HR diagram. What is this HR diagram? When Hertzsprung and Russell independently, they have taken the data of temperature of a star and the luminosity of a star. When they have plotted, the conclusion is they are not uniformly distributed throughout the region of luminosity and temperature. In fact, 90% of the stars, they are lying on a very narrow region called as main sequence, and remaining stars, they are located in giants, red giants and white dwarfs. And the utility of this HR diagram I have tried to explain with the help of some numbers. One can find out the size of the star if you know the value of L by L sun and T by T sun, the ratio. I hope you got some idea about the HR diagram. Two more important selected properties of the universe I will discuss in the next lecture. Thank you very much for your patience. Thank you.